Hello, welcome back to the GR300 Geographical Data Analysis video series for WVU. This is the second of 3 videos looking at Chisquared. The first one we looked at the broad setup. Now we're taking that broad general setup and putting some context to it and putting it into our framework for inferential statistics. So no matter what, for that framework for inferential statistics, the first thing is identifying the null hypothesis and the alternative hypothesis. The null hypothesis is the predictions are good. The predictions are correct. This, at first glance, might actually seem to contradict our approach for everything with inferential statistics of the null hypothesis, nothing interesting going on. And the alternative hypothesis is what we really want. The null hypothesis here, in terms of the nothing interesting, a large part of that is based upon, well, how do you get your predictions? We could have something where we may wish to say, okay, I had that group. We're breaking the study area down into groups, right? And I want to look at the let's say the density of some invasive species by soil type. Soil type being my categorical variable, soil or the species being the density, like the number of plants per square kilometer. That is my my continuous variable. We can then say, well, okay, there's several ways we could then develop our predictions. And that's where kind of the challenge, those are some of the benefit for Chisquared comes into play. I could, especially if I wanted to have something where I'm truly setting a null hypothesis, find the average density across the entire study area, and say the density in each of, say, 4 soil types matches that overall average. That would be the closest to what we expect for a standard, a standard inferential null hypothesis of nothing interesting. My predictions have say there's no relationship here. We could then say, if that is significant, then no, there's not. Those predictions were bad. The problem in doing so from that is that we actually don't know why the predictions were bad. It may have nothing to do with the soil type. They just may have been, there just may be so much variability, the predictions are bad no matter what. Another approach can be to say a group average. And this is the approach that I will be taking in the exercise for Chisquared. To take the average value for each group So if we have this group average, and I compare each individual plot against the group average, then I could say, does the group average actually give a good prediction? that can be a place where chi-squared can fit in and say, in this case, especially if we have a very high p-value, normally we're looking for very low ones to reject the null hypothesis. This could be a situation where if we see a very high p-value, because I now have an informed prediction, and I have a p-value that says that really matches the data well, I'm onto something. This can be a good predictive variable. So kind of to back up or to flesh out in a sense, what chi-squared is doing so we saw the t-test had the t-statistic. The ANOVA had the f statistic. Chi-squared has a chi-squared statistic. This is the Greek letter chi. The chi-squared statistic is based upon how much error there is in your predictions. If your predictions are good, this is lower. If your predictions are bad, this is higher. Although it's more complex than just simply adding up the total error. In large part because it tries to account for the difference in sort of the range of the data, where kind of like we saw with the coefficient of variation, if our predictions are off by 10 or even by $10, let's say, if our predictions are off by $10, whether that's good or bad is really a factor of what we were trying to predict in the first place and what values those are in. If I am trying to predict the value of a gallon of milk, being $10 off is a really big error. If, however, I am trying to predict the value of a house, which can be hundreds of thousands of dollars, now being off by 10, that's really spectacular. So it's not just adding up the error. Chi-squared tries to account for the extent to which values are higher or lower, have a big range or small range. It then it compares it against something called a chi-squared distribution. That, just as we saw with the F statistic, the F distribution changes with ANOVA based upon things like how many groups there are. Well, in this case, it's sensitive to how many predictions there are. So if I'm trying to predict 1,000 values, my chi-squared values are probably going to be larger than if I was only trying to predict 3 values. This accounts for that. What the p-value is then doing is saying what's the probability of getting more error, more collective error, under the null hypothesis. So in that sense, it's saying that's how it's assessing the extent to which the data supports that null hypothesis. If my predictions are good, then there's a very high likelihood of getting more error. If my predictions are bad, then there'd be a small likelihood of getting more error. Well, that's how we would then interpret this p-value. There are two additional cautions about the chi-squared statistic that don't go strictly into the different parts of that inferential process, but there are things to be aware of. So the first caution it only really works if you have positive values. So that is something to be aware of, and especially if you have values that are both positive and negative, that can really start to throw things off. There's also general guidelines about how big your predicted value should be. Typically, that ends up being kind of a rough rule. There can be some flexibility in this. A rough rule of there should be at least 5 for your prediction values. So the predicted values must be 5 or more. It gets back to what I said about how this chi-squared statistic is working. It's trying to assess how much error would be expected based upon the value. So that's where actually doing the gallon of milk example I gave would be bad, would not be the best example, because a gallon of milk is less than $5. My predicted values really ought to be less than 5, and so chi-squared is not an ideal check there. Or I guess you could fudge it by saying the number of cents instead of the number of dollars, which in a way gets to the last caution. You can basically, if all you do is multiply all your values by 10 or by 100, you can change the outcome. You can change the conclusion just by multiplying everything by the same value. That would be something to be concerned about, as a caution to be aware of. It doesn't mean this is a horrible statistic, but that is something that to recognize, especially if you're looking at other studies, to see, is this a way they could have manipulated things to give a misleading result? So those are different, the different ways that chi-squared gets worked out, that we actually make an inference from that, where it's assessing the error within our predicted values. As always, if there are questions, please feel free to speak up in class, to speak up by email, and thank you for watching. I'll see you at the next video.